This is lecture 38, continuing our discussion of device management. We noted that we have a myriad of devices. So we have a wide range of different types of devices, and some are also high speed. So they place a significant load on the system per se. And these devices, for the most part, in modern computing systems are interrupt driven. So polling we do in certain circumstances, but the default norm is interrupt driven, which has been our assumption so far in our discussion of interrupts, including the clock interrupt, which is something that we had to use quite extensively because when we schedule processes, the clock interrupt plays a very important role, as we know. Continuing further here, there's a note here which points out the link between interrupts and scheduling that we already talked about. So because of all these interactions between the different components of an operating systems, interrupt management under device management is a tricky topic. It's a very subtle topic. The review of I/O, that is I/O performing on devices when we use interrupts. So we have a processor CPU that enables a device, and then the device may be asked to read or write, and when it has some event to report, it generates an interrupt, and then we said that the CPU at a high level abstraction performs these operations of fetch, so this loop of fetch, decode, and execute as we discussed, and logically we view as interrupts being handled at the end of this loop. So this loop, it keeps repeating forever, but after we execute an instruction, then the CPU, logically speaking, checks for an interrupt and then takes care of it or knows what to do with it. So that's where interrupts come into play in the global picture of things. Processes and interrupts. So in Xenu, and this is the norm with exceptions in other operating system, we have a process that's running. So unless a kernel is hibernating or sleeping, we are assuming that an idle or null process in Xenu is always running. And by the previous picture, we can view as an interrupt being squeezed in between these two loops that I showed earlier, because an interrupt is handled at the end of this three-step sequence of the CPU. And we are assuming in all of the slides here that when we execute an interrupt handling part of the kernel, it borrows the content of the current process. So the current process executes the interrupt handling code, and we called this approach context borrowing. And we will see that there's another technique that can be used that doesn't borrow the context of the current process, but in these slides, that's the assumption. So please keep that in mind. Historic interrupt software typically thinks that its code was written per device. There was no commonality. It was quite complex and messy. Then code changed, code evolved so that a two-stage sort of system, overall speaking, was implemented or adopted. So a dispatcher that takes care of the first step, and then a second step where a handler comes into play that performs tasks. Now, This terminology can be used in two different ways, and we will see some slides soon where in one form of dispatcher it means that some interrupt is generated, and here is an interrupt dispatcher unit. So here's the dispatcher, and then it decides which of the various interrupt handling subsystems will need to be then invoked. So maybe for clock related stuff, for Ethernet, for Bluetooth, etc., etc., etc. That's one way of looking at the notion of dispatcher, which is the principal way that these slides are using it. But keep in mind that one dispatcher that we have looked at quite a bit is where the interrupt here turns out to be an interrupt. So here's an interrupt, and the interrupt that we have used predominantly is our clock interrupt. And when the clock interrupt is raised, then we know in x86, so this is for x86, through the interrupt descriptor table, we then jump to the clock handling code here. We know which entry it is as we discussed it earlier. And then this branches, because there's a function pointer here, as we know, to the clock dispatch code inside this file. So this is the file, of course. It contains this piece of assembly code translated by GCC into machine code. And this guy handles low-level things, and then it calls a C function called clock handler. So in this scenario, the steps are different. Here, the step one means it is trying to demultiplex. It's trying to determine demuxing or demultiplexing, or to separate what this means into different branches depending upon whether the interrupt is of this type, this type, this type, etc. That's step one here. But even for the same interrupt, there is another two-step chunking that's being done, where this is step one, where typically it's coded in assembly and it takes care of the low-level chores, which oftentimes are common to many of the different devices. And then for the actual heavy-duty handling of a specific interrupt, another function, the handler, is invoked. And keep in mind, these two steps, step one and step two, is for a specific interrupt. So this step, dispatcher handler, can be used in this way, or we can apply this terminology in this way, and certainly we've used it in Xenu for the clock interrupt, or more generally, it starts at one level higher, where the dispatcher then disambiguates which interrupt we're talking about, and then it lets each of the different interrupt types again engage in their own processing, which in turn could have two steps or maybe one step. It depends. So these are all very much hardware dependent. So interrupt dispatcher code, it runs in interrupt mode. So typically, but not always, with further interrupts disabled. And the hardware has to then remember in the case of x86. So always use x86 as a reference point because it makes things concrete. Otherwise, what we discussed would be too abstract. It would be too up in the air. We want to make sure that what we discuss is grounded. And so you can always reference this one specific architecture. And if you know how to do that, then it's fairly straightforward to understand other architectures where some things may be done slightly differently. So in the context of this x86, then we know that an interrupt uses our IDT table per interrupt number, and then it contains a bunch of information, but the one that we care about a lot is a function pointer to the interrupt handling code in interrupt.s. This was an important file that you looked at in lab 2. And so this was the connection between hardware interrupt, this table, which is a software table, but at the same time, it's a software table that the hardware uses actively, and then it jumps to, based upon what function pointer we install at each of these entries, to code within this file, where then those specific interrupts are then handled in this step 1, step 2 fashion that I just mentioned. And when we use the clock dispatcher as an example, then you will find that our clock dispatcher, so this dispatcher code, which is step 1, and then we have clock handler, which is step 2, again a two-step process for every interrupt, or in this case for the clock interrupt. In this case, when you look back into the code here, what we do is we save state by saving the content of the 8 register values. So that's the main principal state, and you know that we do it by pushing the 8 registers. But prior to that, it also disables interrupts. So here you might ask, why is this guy disabling interrupts? Isn't the hardware helping us out by, if there's an interrupt, disabling other interrupts so that this guy can then proceed, not worrying about having some shared data structures be corrupted? The reason is this is very much hardware dependent. In x86, what we ignored, so these are the details that we are not discussing because all the hardware stuff that we discuss is on a need-to-know basis. Otherwise, we would be spending tons and tons of stuff getting more and more expert on what this hardware does, but it would be not much directly related to operating systems, to software. So the stuff that we discuss about hardware is directly relevant to software design, to programming. That's why we are discussing these features. One feature that I did not discuss about x86, but I will note now in this context, is that when we install here this information about what function pointer it has and other pertinent information whose details we still don't care about, but these things that we install, they are called in this x86 Intel jargon gates, because they are gates through which you enter and then perform different things. A gate that's here, another gate that's here, another gate that's here. So you have to pick different gates or doors to go through. So that's the idea of gates. But in x86, there are several types of gates. Two important gates here that now I'm going to mention are that there is a gate called trap gate. So this is for x86, and another one called interrupt gate. Interrupt gate. Two different types of gates. There are more types than this, but these are the two principles, one here, that are relevant for this discussion. They are almost the same, these two types of gates, in terms of what we configure, how we configure it. But the main difference between this and this is, if we configure the entries in IDT as interrupt gate, then the hardware, when an interrupt here is raised, automatically, so the hardware performs the operation CLI. So it disables interrupts for us. So in the software, in this code, we would not have to do CLI because it's already been taken care of. If this guy is configured, however, as a trap gate, not as an interrupt gate, but it's configured to be of type trap gate, then the main difference between this gate is interrupts are not disabled by the hardware. So when there's a clock interrupt, well, there's a clock interrupt, but the equivalent of performing CLI is not taken care of by hardware. So now you can imagine why do we have CLI instructions done inside this clock dispatcher, because the entries in IDT in Xenu, when it's set up initially for x86, they are all set to be of trap gate type. That's the reason. If we had set it to be of type interrupt gate, then we would not have to perform CLI. But then why do we set it up for trap gate? Keep in mind that when we are trapping to the kernel, that's where we use the term trap, we talked about performing system calls. And the system calls are in our picture. Here is user mode, and here's kernel mode, and here's upper half, and here's lower half. And the system call is the interface by which a process switches its mode from user mode to kernel mode and then performs upper half tasks, as we already know. And in that case, when we are trapping from user mode to kernel mode, using trap gate, that is, we do not disable interrupt, that is viewed as the right thing to do. When on the other hand we have interrupts coming up from downstairs, then by default it may be beneficial to have CLI be done by the hardware automatically for us. In that case, those entries would be configured to be of interrupt gate type. In Xenu, we just make everything trap gate. And now the software is in charge of disabling interrupts or not by executing CLI or not. So here the task of how to deal with further interrupts is delegated to software entirely, but keep in mind in this hardware configuration we can seek additional hardware support to get its help to disable interrupts or not. So again, these are all very much hardware dependent features and they can vary widely from one architecture to another. But what are the typical options, how they may be used, these are things that do remain common. The specifics can vary, but the overall generic outline of what is available or what may be available or not, that is fairly common. So going further, so here's a picture of a two-step process where we have a hardware interrupt coming in, and here the dispatcher is demultiplexing, it's demuxing. What is the interrupt? Is it this type, Ethernet, this type, this type? That's one way of looking at what dispatcher means. And then from the dispatcher, we talked about return from interrupt. So these are things that we had to do already at the very get-go. So this is in x86. As you know, I read this instruction because the hardware, again in x86, when an interrupt occurs, pushes, we know, EFLAGs, code segment register, and then, of course, the instruction pointer. They are all pushed onto the stack of the current process by the hardware. So these are three push operations, and obviously they have to be done atomically. And then after we are all said and done, we have to pop them. And these are of course separate steps, and we need the hardware's help to pop them atomically in one swoop without interruption, so that the content, the bits saved on the stack, can then be copied over into the actual registers EIP, CS, EFLAGs that reside on the CPU. So they of course reside on the CPU. The content of these registers was pushed, that is saved onto the stack atomically by the hardware. Now we have to copy them back into the registers here using IRED, also atomically. So atomically doing something is a feature that we need hardware support for in general. So going down further, so here is the notion of an interrupt vector. So this is a very general term. You will hopefully remember it from the computer architecture course. So When we don't want to speak or talk about specific hardware, then we use generic terms, and an interrupt vector is a very generic term. In x86, the interrupt vector for us is this software hardware table IDT. That's where we have configured, or we can configure, for the different interrupts that x86 supports from 0 till 255. Those entries then can be configured. We just talked about making those entries gates to be of type trap gates or interrupt gates, and so on. And this is what this relationship is. So it's a vector, it's an array, it's a 1D array, and we use it primarily for our case with additional subtleties of our interrupts hardware disabled or not automatically, in the principal component being function pointers to the software in the lower half of the code, the kernel, that then takes care of handling the interrupt that has occurred. So this would be like our IDT. So that makes it a bit more concrete than just talking about something very high level, such as an interrupt vector. So going further, and this IRQ, it's just a shorthand for interrupt request, RQI, interrupt request, which is another term that is often used, IRQ, as a index that specifies what interrupt we're talking about. We call this guy just interrupt number because it's plain and it's simple, but you can call it IRQ and it will mean the same thing in our setup. Here's a more concrete picture for our Galileo backends where we have different interrupts that may arise, and then it is not the case where we have now one dispatcher that then branches off to Ethernet, to various serial devices, etc. Instead, the interrupts are not demarked here, so there's no demarks going on at this level. Instead, depending upon the type, for Ethernet, where we installed in IDT, and we haven't done that because it's not coming into play in any specific items that we are doing. For Ethernet, it comes in, and then the Ethernet dispatcher handles step 1 component, and then it calls the Ethernet handler. So here, step 1 and 2 is similar to step 1 being the clock dispatcher, and then step 2 being the clock handler. That's the sense in which the dispatcher and handler term is used in this picture. So again, keep in mind, we're using these terms in two different guises. Here it would be for a specific serial device on which again there's a dispatcher, and then this guy can do some form of demultiplexing and then branch off to the different serial handlers. The one item where we saw this picture prior, or we actually used this picture prior, where here is a dispatcher and then it branches off depending upon interrupt to do different handlers, Ethernet handler or Bluetooth, serial, etc., clock, this type of scheme. We already saw in the context of when you implemented trap system calls in lab 2. In trap system calls, what happened? We created a system call dispatcher, which we installed at a specific entry in the IDT. So just go back to lab 2 if this is a bit vague or you are not sure, and we installed it for a particular interrupt number. And that interrupt number then in this file branched off to this system called dispatcher. Of course, there can be multiple system calls. We only supported for the main problem 2 system calls. And the system call number, like the interrupt number, was communicated via the register EAX. And then the system call dispatcher, whose code is inside here, then decided which of the system calls, that is, which system call 1, system call 2, 3, there are a bunch of system calls. In modern operating systems, perhaps 300 plus is quite common, although there can be fewer. So this demultiplexing, demuxing, or this architecture we have already encountered in the specific context of building a system call dispatch. So this is nothing different from here. We have something coming in. This dispatcher has to then disambiguate which system call we are talking about, and similarly in the case when we are handling interrupts. But with these varied ways of carrying it out, as noted. Here is a picture for our BeagleBone Black backend. So these are ARM architectures. And again, these are very much hardware specific things. And so here the hardware are called exceptions. So again, a term that you just need to be careful about, because in the case of x86, exceptions or faults are used by default in a certain way. But here it's different. So here you have data exceptions, which would be like our x86 exceptions, and then here are IRQ exceptions, which would be like external interrupts. And so here in this architecture, it has this 2-level or this 3-level design, where here it goes through and then there's another dispatcher here per those different levels that then separates between the different handlers. So again, it's very much hardware dependent, and when you deal with this stuff and you want to implement it in that specific hardware platform, then of course you need to familiarize yourself with the design of the hardware, this big picture, and then the details of how to make each of these components work. Like I mentioned, in IDT, there are different types of gates and the different roles that they can play. There are more details like these that are feature bound, that come into play in different architectures that we use in the wild today. Going further down, basic rule of interrupt processing. So again, how interrupts are disabled or are not disabled, that may be something that the software does or the hardware helps with. These are things that are very much hardware dependent. One aspect that, however, is worth here emphasizing is, in most cases, by default, the hardware for the same interrupt keeps that interrupt disabled until the software acknowledges that interrupt. So for example, if you have a clock interrupt that occurred, until such time we acknowledge the clock interrupt, this clock interrupt remains disabled. Other interrupts are allowed. So a packet comes in on Ethernet, that can ring. But the clock interrupt, until such time that the software says it's okay to have another clock interrupt occur, the same interrupt is disabled. And this is so that we don't get swamped with the same interrupt type while we are still trying to handle the previous instance of it. So this is a very common design that by default you are likely to encounter. But again, it's something that you have to explicitly verify, because these things can vary. Let's go down further. And of course, to disable interrupts, we talked about what it means. We are doing process synchronization and in particular we are exercising mutual exclusion. And we talked about two hardware support ways of doing it. One was interrupt disabling, which is what we are actively using here. And then the other one was test and set. And the software way of doing it, of course, is using semaphores. So nothing new is here. We're just reusing what we discussed earlier, mutual exclusion, because we want to disable interrupts so that when a particular data structure is being operated on by, say, the clock dispatcher, not that it is, but suppose it were, then you don't want this guy to be interrupted by another instance of the clock dispatcher, which then changes some value here that this guy hasn't yet fully updated. That would corrupt the data structure. So we are trying to make sure that things are done in an orderly fashion for shared data, and we're using the simplest trick available, which is interrupt disabling. So that's what we are talking about in this setup. Interrupts and processes. So for doing device I/O, so this is for our device I/O. We're doing read. Basically, we are doing read or write. There are other out-of-band operations, but read and write are our canonical examples. So therefore, when a process is doing device I/O for read, then a device may not have data that has arrived yet, and the data may then at some point arrive in the future. When a process performs a write, then the message, the information to write to a device may encounter a buffer, an output buffer that's full. So there's no place to write it. But then again, in lab 4, you dealt with the send system call, which in Xenu by default is non-blocking. But then you created a blocking version as well of send. Exactly the same setup. So I noted earlier when we talked about process synchronization and inter-process communication, so IPC and synchronization, I mentioned that the techniques that we are covering will also, for the most part, apply to device management. And so we are catching two birds, or actually multiple birds, with one stone. And here, how does this relate to what we are talking about here? In the setup of IPC, so for IPC, so here is again our good old picture of user mode, kernel mode. And here we have the upper half, and here we have the lower half. In IPC, when you did send, and you implemented blocking and so on, then this setting was that we had two processes, P1, P2, one a sender, one a receiver, and they're doing inter-process talking, inter-process communication. So this guy makes a system call. So this guy makes a system call send, and this guy makes a system call receive. And these system calls of IPC are implemented in the upper half code of the kernel. For IPC, we don't have to touch the lower half. This guy doesn't come into play. We can all take care of this stuff in the upper half. The scheduler, the guy that's wedged in between, so the scheduler here, and we drew it in between because it's sort of sandwiched between these two halves since they both invoke the scheduler, as we know. But in this setting, the lower half does not get involved for IPC. And we know the techniques using semaphores, using counting semaphores, how to make sure that a message is correctly passed from the sender to the receiver involving only the upper half of the kernel. And what blocking means, what non-blocking means, all of that will transfer over to device management, to device I/O. But what's the key difference? The key difference is because we are now doing device I/O, not just inter-process communication, the source of communication is not something that is, so here is again user mode, kernel mode, and here we have a process P1. Suppose P1 is reading, so this is a reader. So this is a receiver P1. But it's not receiving from a process, it's receiving a message, a packet that's sent over some network. Say Ethernet comes in on this device called Ethernet interface. So this is hardware. It gets stored into a hardware buffer. And then this message, which is stored here, so let me highlight in red. So this message arrives. It temporarily then resides here. It generates an interrupt. So this is the interrupt. And of course, we know that the lower half, this guy, comes into play. Here's the upper half. And so the interrupt is issued. And then code in the lower half, as we just discussed, for interrupt handling, dispatcher, handler come into play, and then this code would have to copy this piece of message from this hardware buffer to some kernel buffer. And here I'm only highlighting a kernel buffer that's visible, so this is the same message that's arriving. It's contained inside this message. It then is stored inside this hardware buffer, and then it's copied over by software from hardware buffer into some kernel buffer. And I will show this thing in more detail shortly. So it travels from this packet to this hardware buffer, from the hardware buffer to RAM memory, because it's kernel memory, and then ultimately this message is destined for some process. Most messages. Some messages where you are talking to the operating system per se are not destined in general to a process. But outside of those exceptions, a message is meant to be delivered to a specific process. And we talked earlier about port numbers, because we cannot use the PID, since the PID is something that we don't have control over. You cannot ask the kernel, hey, give me this PID. You could design kernels that do that, but that's not how it's done. And so PIDs you don't have any control over, but port numbers, these 16-bit numbers, you have control over. And so therefore, there's a binding between port number and PID. So processes are identified by the port number, which then specify what the PID of a process is. So this is an alias of this PID of a process. But the point being, this message ultimately is destined to the reader, to this receiver. So this message then has to be copied over to this guy's user buffer. So this is all the traveling that's being done. But who does the copying from this buffer to this kernel buffer? The lower half, that's the software. That is the code that does it. But the lower half runs in x86 through IDT, which then has a function pointer to a dispatcher code here that performs the operation. But who, that is, which process carries out this operation? We assume context borrowing. The current process, whoever was running, is the process whose context we are borrowing to execute this code. And then after this guy has copied it, the upper half must run, and then it must copy this message to here. So the upper half run is run by whom? The upper half is run by whoever the receiver is. In Xeno, the receive system call, in Linux it would be the read system call, causes a trap from user to kernel, and then it tries to do what it needs to do. If the message is not there, we know that it means blocking and the reader is context switched out. But when a message arrives, then borrowing the context of whoever the current process is, the lower half code runs, and we know that this guy's responsibility is to unblock the reader. Same as send in lab 4, where if the receiver's buffer is full, the sender was blocked. So the sender needed to be unblocked. Who unblocked the sender? The code of receive. So in a similar vein, when a message arrives, then a process runs this lower half code and a process runs the upper half code. So the difference between IPC and device I/O is not that in device I/O processes are not handling messages coming in. No, it's always a process that runs and carries out operations. That's what we emphasized. Except for bootstrapping, no code subsequently is performed not as a process. Some process, some PID, any code, someone, some process executes that code. So that's always a design feature that is common to Xeno, Linux, Unix, Windows, etc., etc. But the difference between what we discussed earlier, IPC, talking between these two guys, and this guy receiving a message, so its partner is some other guy far away, might not be even the same operating system, in which case this operation also involves the lower half, this half, this part. So here it only involves the upper half. Here now it also involves the lower half. And that's the main distinction that we want to keep in mind. But otherwise, blocking, unblocking, who blocks, who unblocks, all of that stuff you already practiced when you implemented in lab for the blocking version of send. And there's no difference at all when we are doing blocking, unblocking, because the event, the message is not from one process on the same OS to another process on the same OS, because the message is a message that arrives on some interface, from some network interface, Ethernet, Wi-Fi, Bluetooth. When the lower half code runs, it's still a process that runs this code, context borrowing in Xeno. When the upper half code runs, it's still a process that runs the upper half code. So therefore, we need to make sure that processes are able to not cause disruptions to each other. And how do we make processes not cause issues for each other? By using the techniques we learned under process synchronization, process coordination. So nothing new. It's exactly the same techniques that now we can afford to reuse when we're doing device I/O. Slightly different setting. It looks like a completely different beast on the surface, but if you look at it from the viewpoint of the internals of what's actually going on, no need to invent new techniques. It's precisely what we've already discussed and covered that we can reuse to perform device I/O. So I'll mention this again, but it's important to get this idea into place because it's something that's not so obvious, but once you get the hang of how operating systems are architected and implemented, then it should by now become sort of obvious. Anyhow, it's something to think about. All right, let's continue further. scheduling invariant. So we want to make sure that we always run a highest priority ready process. So as we here discussed, when we have blocking, unblocking going on, and we unblock a process. So suppose, again, to make sure that this is crystal clear, user mode, kernel mode, a process P1 who does read, who does receive, perform the system call. So this is of course handled by the upper half, but it got blocked. This guy was context switched out because there's nothing to read. No message has yet arrived. But subsequently, a message arrives. So here's a message, a packet that arrives through Wi-Fi interface. Here's a Wi-Fi interface, and the lower half, because it raises an interrupt. That's what we're talking about. So here's our interrupt. Interrupt is raised. So interrupt is raised. Then of course lower half executes interrupt code, dispatcher handler, and this guy then copies the message. This guy, which is saved in this hardware buffer, the lower half code copies it to a kernel buffer. And then the lower half unblocks P1. So P1 is blocked because the upper half, which performs read, blocked P1. So who blocked it? The upper half of the kernel blocked P1, which means it was context switched out. So it was context switched out. But now that a message has arrived, and the lower half takes care of it by copying it from here to some kernel memory, now the lower half notices, okay, this message is destined to port number, say, 7777, and this happens to be process PID 20,000. So this is port number, and this is PID. And who is PID 20,000? Say that this is our receiver P1. So then the lower half notices, oh, P1 has been blocked. It's been context switched out. Why? Because it's waiting on a message. But the message, this message arrival is an event. Like a timer alarm that you are doing in Lab 5 is an event. This is just an event. It's a specific event type. This event type now has occurred. So this event has been generated. The software now kicks into action, copies over here, and it notices, oh, I need to now unblock process P1. So P1 is unblocked. Unblock P1. But who does this unblocking? It's the lower half, obviously, in our setting. And after you now unblock P1, the question is, that's why we're talking about the scheduling invariant. There is some current process running, suppose P55. P55 is the current process whose context we are borrowing to perform all of these operations. But now P1, which was blocked, has become unblocked, which means P1 is ready. And now the question is, whose priority is higher? P1's priority or the current process, P55's priority? And we know that by our scheduling environment, we want to the extent that it's feasible to do, always execute a highest priority ready process next. This guy was not such a candidate because it was blocked. This is only about ready processes and of course the current process. But now this guy has become unblocked, so now it's ready and it's in direct competition with P55 to determine who should run next. And who decides that? The scheduler decides that. That's the scheduling environment. In Xenu, our scheduler is reschedule, wedged in between these two halves. But for this guy to run, someone has to call it, because except for the page out daemon that we discussed in terms of page eviction, all the code of kernel was just a function call, a library. A kernel is a passive library of functions. The same is true, of course, for the scheduler. It's just a function. For this function to be executed, someone has to call it. Some other function has to call it. So who calls it? The lower half calls it. So after the lower half is done, it calls the scheduler so that it readies it, and then that is, it's going to now determine who has the highest priority, and if the newly unblocked process P1 has higher priority than the current process P55, then as a result of this message arriving, the lower half noticing that P1 was blocked, waiting on the message, unblocking P1, making it ready, calling the scheduler, which then picks the highest ready process to run, including the current process. It notices this guy who was blocked earlier, who now became unblocked and ready, has a higher priority than the current process, and so P5 is now context switched out, and P1 is context switched in. And this is all a consequence due to a measly message arriving over some network interface. So here you see all of these various components, including scheduling, again come into play. Upper half blocking, lower half unblocking, all of this stuff has to be taken care of. But nothing is really fundamentally new. We already covered pretty much all of this stuff, except for talking to a device already under process synchronization and inter-process communication. So that's what I'm again emphasizing. All right, let's go further. So that's the scheduling invariant. We know about the null process. There's always a null process that's running, our idle process, in case there are no other processes who are ready inside the system. And one consequence of having always this null process that runs, if there is no other process to run, is that, so this is a property that we want to insist, so that there's always this process, null process, that will run if there are no other ready processes. So they're all blocked, sleeping, whatever the case is. Then this guy becomes current. That's the only time that it becomes current. And now when an interrupt occurs, the interrupts, so here is now the null process in Xenu, so this is for Xenu, and this guy is current. Why? Because no other ready processes at that moment exist. Upper half, lower half. Here is an interrupt. A message arrives on Ethernet. Who executes the lower half code? We are borrowing the context of the null process. So this guy runs to handle the Ethernet interrupt code. But now look at the code to handle the packet that just arrived on the lower half. We must ensure that the null process is always ready to run. It can never block. So the null process can never block in this architecture. By definition, we have this process who never blocks so that it can always run if all other processes are blocked. They are not ready. That means that since the null process could be the current process that's running, whose context we are borrowing to run the lower half when a message arrives on an Ethernet interface, the code, this lower half code here, cannot, under this design, cannot execute, cannot run blocking kernel function call. Because if this were allowed to be coded so that this guy can make an internal, so these are all internal kernel functions. So these are not system calls, these are internal kernel functions, some of which are blocking, some are non-blocking. That's always true of function calls. Are they blocking or are they non-blocking? But we cannot allow this code inside the lower half of the kernel to include blocking kernel function calls, because that could possibly cause the null process to block, which means to be context switched out. But in our architecture, the null process must always be ready. So this guy must always be ready so that it can become current when there are no other ready processes. That is its principal job. And that would be defeated, that would be violated if kernel code inside the lower half included blocking calls. And so this design mandates that we cannot code the lower half using blocking calls. That's what this is indicating. And here it's using the Zenu semaphore calls signal and wait. And here keep in mind that it becomes a little bit imprecise, in the sense that because in Zenu we are always running in kernel mode, so you know all of that already, we are making system calls from within kernel code. So in general, Linux, Windows, Unix, or typical modern operating systems, making system call inside kernel is nonsensical. It makes no sense, as we noted earlier. This is completely nonsensical. Which means that when the kernel itself needs to use semaphores to protect its data structures from itself, because the upper half of the kernel is run by some other process than the lower half of the kernel when we're context borrowing. And so we need to make sure that the kernel also uses semaphore calls to protect it. But we cannot use the semaphore calls that are exported to the user as system calls and call them here inside the kernel. That makes no sense, because system calls are calls that trap, that go through all of this machinery that we discussed in Lab 2 to switch from user code to kernel code with hardware support for trapping. You cannot trap when you are already trapped and inside the kernel. So therefore, you need to make sure that you always have duplicate versions of the semaphore calls, one as system calls that are exported that trap, and others that the kernel internally calls itself, which are not trapped, so that the kernel can make use of semaphore calls. But in Zenu, because there is no separation, in this slide, it talks about the lower half making this system call. So just keep in mind that caveat. It's okay in Zenu to say that, but outside of Zenu, in most cases, this would be nonsensical for the reason that I just mentioned. But signal is a non-blocking call, so that guy is okay to call. But you could not allow wait to be called by the lower half, because as you know, the wait semaphore call is by default a blocking call, except for the guy that calls it first, for example, for the case of mutual exclusion. And if the lower half code were allowed to make a blocking call, here like wait, then it could potentially, of course, block the null process and context switch it out so that it's not ready or current. And that's, of course, not allowed. That's the idea here. So no blocking calls under this design inside the lower half of the kernel. That's the constraint that we have to abide by. So let's stop here and continue next time.